Actually, I didn't know it, but I apparently volunteered to be the chairman because I sat there. I had no idea, anyway, but regardless. So it is my great pleasure to welcome Nadja for her last talk of this school. She will be here next week, right? For the workshop, she will give a talk there as well, right? So for those of you who will be staying, you have a chance to listen to Nadja one more time. For those who are leaving, this is the last chance. So it is the last opportunity to actually ask her many questions, and you should. I must say that I had the pleasure to work with Nadja for many years. I've known her for a long time. She was a student here, just like you guys, and she did ask lots of questions. So that entitles you to ask some questions as well, right? As revenge. So, Nadja, the floor is yours.
Is it okay? Okay. So today we have then the last lecture. I prepared for the beginning something more like informative than really going into the calculations, but we'll get there. But we'll go through some calculations today again. But it's something that I was missing in the other lectures. It was I haven't said anything about platforms or physical systems that they present naturally non-Markovian effects. So then I collected here some different platforms that I think they are like, because we can think about this non-Markovian dynamics, I see it like in two different perspectives. One perspective is I have my system interacting with this environment, and I cannot do anything to really avoid this non-Markovianity, okay? These are the platforms that I will talk about here now. The other perspective is I really want to use this backflow of information, and I will control my environment, or I will do some engineering in the environment in a way to have like some advantage about this backflow of information, okay? So then one thing is like, I cannot give another description because it is as it is. The other is, I want this effect and I will control it in a way to have this effect, okay? So then just these platforms where these things, they happen naturally, we can think about solid state platforms. So models that, okay, physical systems that can be described by these Caldera-Leggett models, which are basically described by harmonic oscillators. Also, you can have very non-Markovian dynamics in Bose-Einstein condensates, with quantum dots, atoms trapped in an optical lattice, and optical mechanical resonators. So if you go to the literature, you will see many works looking to non-Markovian effects in all these systems. Okay, so these are like typical systems where these non-Markovian effects will appear. Also, we can look for this quantum biology perspective. So you have works where they look to these photosynthetic complexes like molecules, and they will be interacting with some phononic environments, and there they observed non-Markovian effects. And finally, we have quantum optics and these photonic crystals, where we will also see like it's hard to get rid of these non-Markovian effects. Okay, so just to give you a little bit of what are the platforms where these effects are appearing. But if you want to see like more in the other perspective, which is I will do some engineering or I will do some experiments simulating some dynamics, then most of the works they are done in optical platforms. Okay, so many of the experiments they are done using light and photons, and yeah, they are done in optical platforms. Okay, this is for just to give a little bit of more physics than calculations. Do you have any question, any comment in this? Yes? With microphone or chair? You have to. No. Okay, I'll joke. Achei que é você que. Do you think it's easy to be a chair?
We've seen in other presentations the idea of using quantum computers to simulate or emulate other systems. If I have a Markovian system, my computer or Markovian system, could I emulate non-Markovian systems? Or if I have a non-Markovian system, could I emulate Markovian systems?
Very good question. If I have a non-Markovian system, yes, I can emulate a Markovian system. This is one way to do this is like by this coarse graining. So I imagine that the thing that is giving me this memory is just some correlation time, but you can decide to look to larger times, like your interval will be much larger, so you miss these correlations. So then you are emulating Markovian by a non-Markovian system. The opposite, I don't think so. You really have to like know Markovian. And this is a big challenge also for computer simulation, that's how you simulate a non-Markovian using a quantum computer. So there are some works, but this is kind of still an open question. It's really hard to simulate non-Markovian dynamics. When I'm talking about like molecules, like big systems already, okay? Cool, thanks for the question, good question. Any other question? No. Okay. So I told you also that I would talk about applications, but I decided, because of the time, I decided more to be informative and not really go into the details about the applications. But here, I'm talking about this perspective, I'm thinking about this perspective where backflow of information will be used to do something better than if I didn't have this backflow. So one part of these applications is about quantum thermodynamics. So they were able to show that you can have like more efficient quantum heat engines if they have a specific non-Markovian dynamics, okay? This is also, they are not like general results, it's just that they could find one situation where they could make quantum heat engineers more efficient, so they could extract more work. So here I have like 2 examples of works doing this. So this is one of the applications. Another application is thinking about correlations. So they could also show how to preserve quantum correlations and coherence if you have a specific non-Markovian dynamics. So this is a very recent result from last year. Also, I think I like also this result where they can use non-Markovian dynamics to detect genuine multipartite entanglement in 3-qubit system. So detecting multipartite entanglement is not a trivial task, and they show how to use this non-Markovian dynamics like to be able to detect this genuine tripartite entanglement. Also, they show how you can use non-Markovian dynamics to control systems, to have a better quantum control. So I'm really not going into the detail, I just want you to convince that this non-Markovianity is kind of a resource. Of course, if we talk about resource, we have to be a little bit more precise, but in a hand-loose way, I want to convince you that non-Markovianity is a resource for quantum information protocols. And also there is this work where they show how to that like non-local memory effects, but this is connected what we are talking as defining as non-Markovian dynamics, allow perfect teleportation with mixed states. This is something that we didn't know how to do, but then with non-Markovian dynamics we know how to do. They have a protocol how to do this. And finally, I will do some advertisement here. Well, there is this work from Carlos Pineda where they use, the title is Measuring and Using Non-Markovianity, and here they are proposing a protocol how to store information in a more secure way, and this protocol is called the Quantum Vault. And recently, this is just a work we put in the archive last week. And I wanted to mention it because this work started in Paraty, 2019. Santiago came here for the school, and then he spent 1 week there in Recife with me, and we were talking about these multicore fibers, and also non-Markovian dynamics, and then we came up with this idea of implementing this quantum vault using the multicore fibers. So it's nice that Steve is giving this course, because I'm also learning more what are these the properties of the multicore fibers, because I want to start presenting this work. But okay, I just had a model where I was working a lot with, which are these collisional models. I will talk about them today. And I had like specific dynamics, and then Santiago, we were talking how to implement this specific dynamics in the multicore fibers. And here's just the result. So you can see that, okay, I used then some specific interactions between the cores, and I can start then with some information, which is like the password. And so time is passing, and this information will be kind of hidden. And at the end, like at the end of my time, or at the end, imagine that is like something that is closed. I mean, that's after some time it's just open, and the information will be there saved. Okay, kind of like a safe. So someone will be presenting this work here next week.
So,
No, I'm not anymore.
yeah.
Kay was presenting a poster related to the core, root core fibers,
Yeah, but that was for.
another work.
Daniel was going to come, but he's going to Vienna as a postdoc.
That's it. Okay, anyway, so the paper is in the archive, and I hope to be published soon. Okay, but just, it was some advertising. But just to convince you about this, this way of seeing non-Markovianity not as a damaging effect, but as a resource for quantum information protocol. Okay? So then, starting really the lecture today, I want to talk about these collisional models because I think they are very nice toy models to investigate non-Markovian or Markovian dynamics, and they are quite simple. So this was like, when I was preparing this course, I thought, what are the tools that I wanted to give you that I think it will be important if you decide to work with quantum system dynamics. So my first tool was, okay, we have to formalize it, maps, CPTP maps, linked blood equations. Then, how we detect non-Markovianity, because when we start studying these things, so you read entanglement in one article, distinguishability in another, so these things are very confusing. So I try to compact all this information in a way that you can relate them. And finally, I wanted to give this model because, yeah, I think it's a very nice model. So this is the first paper where they just showed that with collisional models, it's possible to simulate non-Markovian dynamics. And these are just the references that I used for this lecture, so this is the first paper. Then our work, so it's nice that Marcelo presented me because it's our work, oh no, not this year. It's our work that we did together in the time that I was in Niger. So we are just using these collisional models to investigate this transition from Markovian to non-Markovian. And as I will also tell you, there are different approaches in the collisional model. So this is another result from Ciccarelli, Palma, and Giovanetti, where they looked for, it's a collisional model, but in a different way. So, okay. So the references will be in the notes in the internet, I just wanted to mention them. So, what is the collisional model? Well, I have my system, as I always have. And now my environment, is just, I will treat it as different particles. Omega 1, omega 3, and whatever, omega n. And the system will interact with each particle of the environment once and only once. So you can think like the system is going this direction, and then it's interacting with the next particle, and then it's interacting with this particle, and so the particles are just passing by, and you are not interacting with them anymore. Okay? So I can say that like the environment is discretized in these particles, so this is like the big system of the environment. And just initially, I will think about the state of the environment. So this will be my first approach. It will be just constructed by a separate state. So all particles of the environment, they have been produced in the same state initially, okay? And sometimes I will just use this representation. So this means that all particles, they were prepared in state omega, okay? So this is times omega times omega times omega. Cool. What happens then with the dynamics of the state when it's interacting with this environment? So I have some Hamiltonian interaction, Hamiltonian of interaction there, which is defined this U. So this U is. Then I can then look to the map, look into the evolution of this big guy, where I have then, okay, as I said, this discretization of the environment is kind of giving me the discretization of time. Like each collision is giving me an interval of time. Okay? So I have delta t, 2 delta t, 3 delta t, 4 delta t, and it goes on. So then how do I write this? And I have here. So each time the system is interacting with one of the particles and is described by this U. So the first collision is just described here. I have this U1. So UI is given by delta T Hy. So this is the interaction between system and particle I, okay? Whose particle I. So then they have here my initial system, the environment, and then the dagger of this. And also that. Okay, so I'm just describing this interaction. So if I just have one collision, the resulting state is the same thing that I had before, but just with one particle. This is the easy thing. Dagger. Okay, this will give me the map in time from 0 to delta t. Okay? So, and if I have any collisions, what do you say? What do you think? It's the map. If I have just followed these definitions. Like, what I want is rho n times delta t, or, yeah, what is rho n times delta t? Like, if I have any collisions, what do you say about the final dynamics, final evolution?
You apply the map n times?
Exactly, I apply the map n times because I just described one collision. So the system, it was correct. And because the system just interacts with one particle, then it will interact with another particle that's exactly the same as the particle that he interacted. Same over, So you just apply the map n times. Delta t. So what I'm doing here, which dynamics I'm describing here? Or can also represent it like this. What is this dynamics, guys? What would we say? I will just represent it here or describe it here. just the map applied many times. This is a completely divisible map. Okay? Cool. So already see like a way to describe a Markovian dynamics using the collisional model. I just choose some interaction and choose some initial state, and the only thing that I have to guarantee here is that all the particles of the environment, they are not correlated. I described it in our, well, they are not entangled. It could be there are some correlation, but they are completely in a separable state. Cool. So then let's start now how we can change this model, these assumptions, in a way that I will simulate a non-Markovian dynamics. And for this, so I want to look then, I will choose some dynamics and I will show you how do we, using the collisional model, we can achieve these dynamics, we can simulate these dynamics. And from this, I want to grasp what are like the two main ingredients to use the collisional model to be able, to use the collisional model in a way that I can simulate non-Markovian dynamics. So the evolution that I will choose, I will just look for qubits dynamics. I was doing everything for qubits just because it's like simpler, but okay, the collisional model doesn't have to be for qubits, okay? We can go for higher dimensions. But I will just choose this map here, which is already similar to the map from the first lecture. And this is a very indivisible map. Very non-divisible. Why? I'm assuming Qx, Qy, and Qz that they are different than 0, okay? So they can never be 0. They sum to 1, but they can never be 0. So why this is a very non-divisible map? Any guess? Well, look to what happens when I just do phi 2 times. I have Qx, and I will apply sigma x to all this Qx, sigma x, rho, sigma x plus. I will just write it once, okay? Plus Qy and sigma y apply to the same, and also Qz, he was Qy, sigma y, and Qz, sigma z apply to this. What is sigma x applied to sigma x? What is it? I should turn off the internet. Okay. What is sigma x applied to sigma x? Identity. So what I see when I try the map 2 times, that I have here Qx going with something that is rho. Then I have sigma x times sigma y, which means that I have sigma z, and so on. So I already find a term that is not going with any Pauli channels. And I already told you at the beginning, assume that Qy, Qx, and Qz are different than 0. So you're seeing that if you apply 2 times your map, you don't recover your map or something similar to your map because you have a term that is not going with any of the Pauli channels. Okay? So this is already give you like an idea why this is a very non-divisible map. So because I applied it twice and I don't get anything similar to it. Okay? Cool. And also you can, for qubits, you can show that apart from a unitary, any non-divisible map can be represented by this map. Okay? So it's quite general. This is another result, but just to inform you. Okay, let's see then how can I, with the collisional model, simulate this guy. Because if I do, I'm already simulating a non-Markovian dynamics, and this will give us the ingredients that we need. So one collision. I just want that my map apply to row 0. And since I'm discretizing the time, this collisional model, when I have one collision, one delta t, I can write phi delta t, or I will just write phi 1. Okay? Because then 2 collisions phi 2, 3 collisions phi 3. I'm not really interested about this delta t. Okay? It's just fixed. So it's the same thing that I already said, the reduced dynamics of the interaction of the system with one particle. And here now I start to have to make choices in a way that I want to reproduce the dynamics that I showed you. And the choices that I will do, okay, the first question, what is a unitary evolution that I can simulate the evolution there? And this is related to some I'm using let's see. Support with some operator which is like this. So this is one of the elements of the Hamiltonian of interaction. So depending if my environment is in state X, Y, or Z, the system will suffer one of the Pauli channels, okay? So here I have X, Y, and Z. They are just related to, okay, they are just forming a basis. It could be 0, 1, 2, but I just decided to use X, Y, and Z because I want you to remember that when I have the environment in state X, you apply a sigma X. When I have the environment state Y, I apply sigma Y, okay? But they are all, it's not related to the position, it's related to 3 discretized levels, okay? It's a Q-trix here, okay? Just to make sure. Okay, we can check and you will be able to see that this operation C has a nice property because if I look to C squared, I get sigma X squared times X, sigma Y squared times Y, and sigma Z squared times Z. What is this operation? What is it? If I have sigma X squared times X, exactly, identity. And this is a nice property because then I can extend the unitary operator, who I'm not using times, is identity times identity. One is living in the qubit space and the other in this Q-trix space. So then I can expand this unitary operator, which would be C. And okay, this is a very easy, okay, this is not the right way to say it. This is a very common exercise in quantum mechanics course 1 to do the explanation of a Pauli channel, the explanation of a Pauli channel. So what is the answer? Because that's why I just did it for this sum of Pauli channels, but it's the same that you already did in this quantum mechanics course 1 when you have the exponential of sigma x. So what is the answer? That's why I show that C squared is equal to identity, because there also it's important that the Pauli times the Pauli sigma x times sigma s is identity. So what does happen when you expand it, the exponential?
You get cosine and sine.
Exactly, you get cosine and sine. So you get cosine with the quadratic terms, and it's all they go to identity. So you have here cosine delta t. Going with C. Okay? So another way to write it is that I can write it in this way, where k is equal to x, y, and z. Okay? So now what I need is that, okay, this is the interaction Hamiltonian. I have also to define a different environment, because as I said, if I just had that environment with separable state, this will not give me a non-Markovian dynamics. In the way that I do it is, I need an environment that always when this particle of the environment is in the state k, then the system will suffer a sigma k rotation. And this with probability qk. Remember the first line here, it was qk sigma x rho sigma x, qy sigma y rho sigma y, qz, okay? So I want to recover this information. And for this, I will choose the environment states as this. So the only thing that I'm choosing, I'm defining about this environment state is that it has to fulfill this condition. Okay, nice. So now if I put everything together, let me check what is like one collision again. The minus is wrong here, but okay. So what I have then, okay, I have this partial trace. Then I have this operator, which I just open it. Do I need this? Now it's C, rho. And what I can, if I just do these calculations, what you can see is that the result will be okay, because the terms that they are going with sigma k, they will also going with k. So when you just multiply, you have this product, you just have the same k, so that's why you just keep the probability, the qk. Is it clear? Because here I have this sigma k going with kk. So if I multiply, or it could be other index, but when I multiply index since they are orthogonal, the only terms that they will that I will keep are the terms where these things are equal. Okay? Cool. So the only thing that I have to do now to recover what I had before is I have to choose delta t equals to pi over 2. And then I have exactly, because this is just, remember cosine delta t, identity plus I, delta t, sigma k. Okay? So I was able, if I choose delta t equals to pi over 2, then I can recover exactly the map that I wanted. Is it clear? Nice. So, if I go, of course I will want to go for more collisions, and then things will get, because this kind of is strange that I will have this delta t equals to pi over 2, this doesn't seem very small. Pi over 2 is kind of a big number. So, if I have any collisions, then I can relax this delta t. It can be something smaller. So then, like, my total interaction Hamiltonian or my unitary operator will be very similar to what we had before. So we are just applying this. As I said, for each collision, I have one unitary operator, okay? So system interacts with one collision, system interacts with the second collision, a second particle. The same thing that I explained. So I will have then something that is sigma k. Okay, this will be particle n times this will be particle 1. Okay? So the same thing as before. And then I can, if I multiply what is acting on the system and what is acting on the environment, I can group them in a way that I have n times delta t, sigma k, times k, or k n times. And here also. So again, I need the same condition, which is always, and I have all my system, all my particles from the environment prepared in K state. They will appear, this component will appear in probability QK. Okay? So the same thing that I had before. And now I can already get, because if I just have one particle, I cannot really talk about correlations. Okay, 1 degree of freedom. I cannot really talk about correlations. So what is this state where I have this, that fulfills this condition here? What can you tell me about this state? If you have to think about an example of a state that fulfills this condition, which state comes to your mind? Maybe it's easy to think about just two particles. Think about something like this. Which states give this, fulfill this condition?
Maximally entangled.
Cool, maximally entangled states. So one possibility would be the state is this one. Okay. Yeah. Is this the only one? Are there other possibilities? Or is it clear to everybody that this guy here will fulfill this condition? That these things are connected? Well, just look to the density operator of this pure state, and you will see that you just... Of course, you have other terms, not only the diagonal terms, but if you just look to the diagonal terms, the QK will appear there in the diagonal. Okay? The other terms, they are also there, but they don't make any difference because of the partial trace. They will just be, they are not contributing. But what is the other possibility where I have also all this QK appearing in the diagonal? Mixed state? Where I am. So I can think about that. Exactly what I said, just with a state with just diagonal terms. Okay? And this will be a separable state, but with correlations, because I always have the kk terms. I don't have the other terms. I don't have kj, kj. I don't have kj, jk. I just have the kk terms. Always, if you think about, if you put 0 and 1, it's very clear. I just have the 0, 0, 0, 0, 1, 1, 1, 1, 1. I don't have any other term. So always in the system is prepared in 0. All the neighbors, they are prepared in 0. Always when the first one is prepared in 1, the neighbors will be prepared in state 1. So this is correlated, it's a classical correlation. Okay? So then, now I have the ingredient that I need. It's already like showing us the ingredient that we need. For having a collisional model and be able to simulate a non-Markovian dynamics, I need some interaction, which I will talk a little bit about it in the final minutes that I have. But also I will need correlation. It can be classical and it can be quantum correlation. But I need correlation between the particles of my environment. Okay? Just to finish what I started, again, if I just see what is the map from n collisions, I won't do the whole thing, but what's this map, n times delta t, as you can imagine, is very similar to what I did in for one collision. And as I said, here I can choose delta t over n. So when I have many collisions, my intervals they can be very small, as small as I want. So it's depending on how many collisions I have. And then I recover this very non-divisible channel, which was what I wanted. Okay? Just choosing delta t equals to pi over 2 over a. Okay. So then I have this, I will put like here, the two ingredients. Note here that the Hamiltonian of interaction, it wasn't anything, it was something special in a way that always when I have my environment prepared in state X, I have sigma X. Always when I had the system prepared in state Y, I have sigma Y, and so on. And as I said, that example of non-divisible channel is quite general. Apart from a unitary, all the non-divisible channels for qubits, they are represented by this qx, sigma x, blah, blah, blah. So at the end, something that is appearing in most of the collisional models when they want to simulate non-Markovian dynamics for a qubit is this structure of a conditional operation. If my environment is state 0, I do this operation. If my environment is state 2, I will do this operation. So this is a common ingredient in all the models, okay? So then one ingredient is conditional interaction. And another one is some type of correlation. So then we have like 2 ways of doing this. We can start with my environment already correlated, or we can create correlation in between the evolution. Okay, these are the 2 strategies about using collisional models. So I will just first explain the strategy when I have initially no correlation. So my system is just the state 0, and the environment, as we already, okay, I will put 0, I will choose. But then how can I create correlations in between? What would be an operation to create correlations in between? So I collide, and I have to do something because for simulating a non-Markovian dynamics, I want these particles of the environment to be correlated. Gases, we saw some operations that they can correlate things with the forces. A synod, but it's not a synod. But the synod is a very good answer. Another one. Oh? They have to see, just see, yes, a condition of Z, which is similar to a synod, but no, is a swapping operation. I will not do it because, so what I have is that the structure is similar, so my system will interact with the particle of the environment, but before it interacts again with the second particle, there will be a swapping operation between these two guys. And then when the system will interact with the second particle, it says that it will interact with particle 1 after already it interacted with particle 1. So you have some memory there, okay? And this will always happen. So interaction, swap. Interaction, swap, okay? And then if I do things like this, of course I can put some stochastic element, because if I'm just swapping, then the system will just see the environment always like the same state. It won't help. And then to give a little bit of the stochastic feeling, my swapping is not perfect, okay? So the swapping, operation between system, like this, system and particle. No, the swapping between particle, because the swappings are between the environmental particle, okay? Between particle I plus 1 and I is just with some probability nothing happens, and with some complementary probability the swapping will act. Okay? Then if I do this, I would see, okay, the final state, the final evolution, just without tracing the degrees of freedom of the environment, just if I think about the final evolution of the big thing, the environment and the system, will be just swapping between n minus 1, system interact with particle n, and it goes on like until, okay, at the beginning, system interacts with particle 1, and I have swapping between particle 1 and 2, and so on, okay? And this will be applied to the initial states. So in this way, I can start without correlation, but correlation will just be created during the evolution. Okay, here's the data of this. And if I do this, I will have, okay, since the swappings, there is always a probability that nothing happens, we will see that there is some term that will stay more similar to what is like the Markovian part, because if I just, the swapping is not doing nothing, I just have like my environment without correlation. This is just a Markovian dynamics, a completely divisible evolution, okay? So I have one part that will go with 1 minus p, that is always, I'm not creating any correlation, and I have another part that is creating correlation. So if I just apply all these things that I have defined, so at the end what I have, I'm more like, again, I'm not really going to all this calculation because I think it's already too much here. But I have 1 minus p. This is the result, okay? Where I will explain what this is, this epsilon map, J. This is the epsilon map, is just the map when I trace the degrees of freedom of the environment when I apply the unitary map, not the swap. Okay, so it's just as interacting with particle n j times, or interacting with one of the particles. I don't like the notation, but I'm just repeating the notation of this statement. It's just one interaction applied j times. So what I see here, I just wanted to comment a little bit the result. If p is equal to 0, what I see, I have this, what is left is j equals to 1, because look here, if p is equal to 0, the only term that is different than 0 is when j is equal to 1, because then I have 0 like to the power of 0, okay? So then when p is equal to 0, I have just one term here left, here will be 0, so I have then the evolution will be given by just the map applying to state n minus 1 delta t, which is just a Markovian dynamics, okay? Because I'm just applying the step n times delta t, just depends on the step n minus 1 delta t. So this is exactly Markovian. If I have p equals to 1, then it's another case, and then I can just see, okay, this first term is 0, and then I have this here, which is just a map applied to row 0, so it can be a Markovian or non-Markovian. I cannot really say anything just looking to this structure. But it's for sure not fulfilling the Markovian condition just looking at it. It's just a map applied to row 0. I have to really check if the map is divisible or not to be able to say something. Okay? So I'm really going into two different regimes. Oh, Chairman, como é que está o tempo? I think we started with 10 minutes late.
Yeah, so
I have 20 minutes?
something like that.
Okay, that's good.
21.
But one question that we had when we were looking to this model, and something that I want to tell you, is that is really just correlation enough? Because I convinced you that the conditional interaction, it makes sense to have it, but if I have this conditional interaction and correlation, is it enough to have a non-Markovian dynamics? So, so this one I want to answer. Is correlation and how to simulate non-Markovian dynamics in a collisional model. So then, to be able to answer this question, I want to use a different model, which is kind of similar, but my Hamiltonian will be, well, because there, my C operation, I just have, if I have the state in my environment in state X, I will do sigma X. If I am in state Y, I will do sigma Y. If I am in state Z, I will do sigma Z, okay? I will change it a little bit. I will put a new ingredient, which is, if I'm in state 0, I will do identity. So I'm including the possibility of nothing happens. So there was a motivation behind it, but because we wanted to really recover masses equations, and it was important to recover masses equations, but okay, now it's not so relevant. Okay? But then what we can see is that, okay, very similar conditional interaction, and my environment, I will start with one collision. So the thing that we want to answer is if we need correlation or not. So you can already guess that what I want to show you is that I will use an environment with correlation, and I will be able to have a Markovian dynamics. So, okay, I think you can guess already that the answer is no, correlation is not enough. But this is a very specific case. But this is nice because that's why I like collisional models, because since you can separate interaction, environment state, these things are very clear, so we can get a better idea what is really causing this non-Markovian dynamics, okay? So then for one collision, my state of the environment will be, it's similar to what that we had before, but again, I have kind of a differentiation between the sigmas, the Paulis, and the identity, okay? So the Paulis, they happen with equal probability, but the identity will just happen with the complementary probabilities. So then for one collision, the evolution will be given, okay, I won't do everything again because this is very similar to what I did before. But as I said, you can see here the result. So with probability pi, they will suffer one of the Pauli channels, and then complementary probabilities, nothing will happen. Good. So if you want to talk about correlations, we have to look for more than one particle here. So we will look for two collisions. And then I will choose my environment state. I will choose a pure state. Does it have to be a pure state? No. It's just because I wanted to do this as simple as I could. In the paper we are looking to different things, but here I just wanted to keep it as simple as possible, so that's why I have chosen the pure state, okay? But I will work with something that has correlation. So if I have my environments in state 0, 0, nothing will happen. I have also the probability that nothing will happen in the first collision, but something will happen in the second collision. And I have also now, I want that if something happens in the first collision, like the same type of rotation that it suffered in the first collision, it will suffer in the second collision. Which is very similar to the first example that I gave in the first lecture, was if the photon is coming, I put some half-wave plate oriented in a way that it will do sigma x, and if it passes here, it will just pass it in another half-wave plate oriented in the same way. So it will suffer sigma x, or sigma z, okay? So this is very similar. Because I just have this term here, and I don't have the terms 1, 2, 2, 1. Why? Because I just wanted it to be like very correlated when I have when it suffers some rotation. Is it clear? So I do have correlation. If you just choose P equals to 1/2, then no, 1/2 is not good. If you just choose P equals to 1/2, then you see that it kind of, okay, it's not it's just a Maximilian state, okay? So that's why this P is giving me like, it's a correlated state, so I can go for, if P is equal to 0, I just have the 0, 0 state. So it's just, I'm inseparable and entangled. I can go from two regions, okay? This P parameter. But I have correlation, but I don't have anti-correlation. In a way that I don't have the 1, 2, plus 2, 1. This is just specific about the model. Then what is the state that I have after two collisions? So what I'm calling rho 2 times delta t. What I see, let me just, so with probability 1 minus 2p squared, because when I do the whole thing, I have the density operator representing this state omega, not only the pure state. So that's why this thing appears as square. Nothing happens with this state. Then, as I said, I have a probability that some and to make things at some point, okay guys, I'm carried and you are also carried because nobody corrected me. But I have pi, and at some point it's just started to appear this p because I have chosen, just to make the calculations easier, p1, two things. I'm looking to p1, p2 equals p, and I have chosen t3 equals 0. Okay? So, yes. Anything that I went through without explaining? I think so, but maybe it's good for time for questions. If you have any question? Okay, then I have this, okay, then the final state here with probability 1 minus 2pp, which because it's just connected to these terms here, they will just suffer one operation, either sigma 1 or sigma 2, or I can choose sigma 1, sigma 2 to be sigma x, sigma z. Okay, the notation is and I have with probability 2p squared, they will suffer sigma 1 and sigma 1, or sigma 2 and sigma 2, Pauli channels, they just identity. Let me just see the notation I used for one collision. Okay, I'll put here sigma x. It's because I was using pi sigma I, that's why I just, okay, this. But okay, I will just have this 2 times rho. Is it clear? So either nothing happened, or they will suffer one rotation, or they will suffer 2 rotations, but it's the same type of rotation, which will be sigma x times sigma x, or sigma z times sigma z, which is equal to the identity. So let's rewrite a little bit these things. I will put in I will just look to the terms that they are going with 1 minus 2p. So I have here rho 0, and I have these guys here. I will just collect them, I will put them together. Which state is this? Who is this guy? Nothing happens. The cat suffers sigma y or sigma z.
Heavy food and gas.
Huh? A what? A mixed state, probably. But how is this connected to the other things that we defined here when we were talking in this moment? The state of one collision. The resulting state of one collision. So here I already see I recover rho delta t. But I have also the other terms, which is here I have put here I have 2 times this, I just wrote it once, so I still have one term of it, so I can put together I have to write it here. And the last term. So if this seems non-Markovian, because I just have 1 minus 2p times the initial collision, the state after one collision, but I have also the other terms that they are still connected to the initial states. So this is not, it doesn't seem like divisible. It's true. But if I choose sigma 1 equals to sigma 2, then what I have is that this part will be 1 minus 2p, p. Here will be 2 times sigma rho sigma plus 2p squared, 2 rho. And I can then put them together, put 2p in evidence, 2p. Yeah, I can just sum this 1 minus 2p p squared, it will just sum with this, then it will remain 1 minus 2p squared, so I can put this yes, this is a different way of writing it. I think it is clear, no? I just put this 2p here and 1 minus 2p here. So, and this is exactly sigma 1 collision sigma. So, if I choose sigma 1 equals to sigma 2, then I see that I'm able to produce to know what is the state in step 2, just looking to the evolution, a map applied to step 1, and this is a Markovian evolution. So I have correlations, but if I made some changes in the conversation. First, I have assumed, okay, P1 is equal to P2, okay. But then just to really get the Markovian, I had to assume sigma 1 equals to sigma 2. So what we see then in this collisional model is that it's not enough that you have an interaction which makes identity and 1 poly. I need at least 2 polys to be able to recover non-Markovian dynamics, okay? So just correlation is not enough, and I need something, the extraction of the Hamiltonian, to be able to describe non-Markovian dynamics. I need this more than 1 poly channel, okay? Which is something I already could think about, because when I started with the first evolution, this non-divisible Qx, sigma x, I said, you assume that Qx, Qy, Qz are different than 0. And what I did here is assume that just one of them is equal to 1. So I cheated. But okay. It's it took us some time to understand this, and I think it was a nice thing to present here. So then this will be just, if I have rho t, 1 plus 2p, rho delta t plus 2p sigma rho delta t sigma. So I just had a Markovian dynamics. So with this, I want to finish the course. Maybe we can open for questions. I will summarize, and then I want to show you something else. Not about physics, about other things. Any question? Good. Ivan.
Hi, Nadja. Maybe you talk about this in the last, but are you making some assumptions about the coupling between the qubit and the scylla, or it can be general, or related some to delta T, maybe?
Very good question. Here I'm not doing any assumption, like I have this eta parameter somewhere and I haven't said anything about it. This is important if you want to recover master equations, because then you really need, like, the interaction, it has to be weak, like in each step. And then you have to say something about this eta, the interaction strength. Okay? If you just want to say about Markovian and non-Markovianity, you can even have a Markovian with this eta big.
Okay, it's because if as Markovian equations as related with the how strong is the coupling between the system and environment, maybe if this G is very strong, can you recover get a non-Markovian evolution just from this, or you
just to have this eta big, like it's not enough. You need that's why I think this collisional model is nice, because you see that it's not only one element that is giving you Markovian or Markovian. So it's not only the strong interaction. Strong interactions, they are very typical in non-Markovian scenarios, but it's not the only thing. Okay?
Just the last one, sorry.
Yeah, sure.
A curiosity, actually. In these models, can you account for like external fields to get like master equations?
External what?
Like pulse, you can.
Yeah.
Okay.
They seem kind of stupid, but they are very general, these collisional models, okay? So you can model any Hamiltonian, like any Hamiltonian that you want. So I have chosen this conditional interaction, but you can model other things. It doesn't have to be,
Nice.
okay?
Nice, thank
Yeah. Yeah, something that I haven't seen, but there are, it's not, it doesn't mean that it doesn't exist, is collisional models for continuous variable. But probably it's possible also to do it. Okay?
Hi, Nadja.
Yes.
I was wondering, is non-Markovianity a quantum property? Do we have non-Markovianity? Do we see it in our everyday lives, like classical dynamics, or?
Sure, yes.
Can you give some examples? I cannot think of anything.
I'm sure. How did you get to
No, my baby, she wants like a physical model with no
Yes,
Markovian. Quantum Brownian motion is Markovian because the chess to go to one direction or the other. A very typical non-classical, non-Markovian. Joe, do you have an answer?
It's just that when I think of Newtonian mechanics, things are deterministic in a sense, and then can you be non-Markovian? Yeah, it's also
It's okay. You are thinking about stochastic process. In both scenarios, you regard a stochastic process where, okay, if it's deterministic or not is a discussion, but you have to like probably to go in one direction or in the other direction. So yeah, you can.
Actually, I would claim that it's the opposite.
Everything is non-Markovian.
It's very difficult for you to have a real Markovian process. In the sense that Markovian means really no, so it really means that like what happens now only depends on what happened immediately before. Or in this picture that Nadja is giving, means that if you have a discretized sequence, so that's a Markov chain, right? The next step of the sequence only depends on the previous step, the state of the system in the previous step. And actually most of what you know, so for example, all behaviors that you have that are exponential, typically the exponential behavior is an approximation. The exponential behavior will give you a Markovian, will come from a Markovian map, typically, but that will probably be an approximation of something that is not actually an exponential behavior. So exponential comes from a rate equation, very simple rate equation, right? The derivative is proportional to the quantity. But that is probably, most probably an approximation for whatever you have.
Yeah, okay, I see. It's just that, and then it feels to me that the non-Markovianity comes from our inability to properly describe the system and the dynamics, and not something fundamental. Am I correct, or does this make sense?
The non-Markovian?
Yeah, in this example, for instance, if we could describe the whole system and it's closed, that won't be like dissipation or stuff like that, or.
Okay.
Yeah, so
Well, if you go back to unitary evolutions, like it will be Markovian for sure, yes.
And it's artificial.
But this is nice because this is the. Sorry, Joe.
The unitary transformations are artificial in nature. You will never find unitary transformation for free. It depends on the model. And following the same steps as Marcelo told us, Nico van Kampen has a very nice paper published in the Brazilian Journal of Physics, describing that nature is mostly, everything in nature is non-Markovian. Well, if you go to an idealized model where you know all the degrees of freedom, okay, it's Markovian, but it's an idealized model. No.
Okay.
We have one question first.
Yeah, in the extreme case, you have to go to the whole universe to have a Markovian. So I think it's
all the degrees of freedom.
Yes.
Everything is Markovian.
Okay. Is there one question? Okay, I want to finish the course, but I wanted to show. Can I finish it, Marcelo? Because the time is done.
I thought you would say I want to put everyone to dance, and that's what we should have done in the beginning of the class.
Yeah, they were all kind of sleeping, I noticed. I wanted to make also some advertisement about something that is not connected to quantum information, but I think it's really nice. This was an outreach project that I have together with Gabriela Barreto Lemos. And we wanted to convince students that physics is cool and it's not boring, so we were like doing a dance course, dancing frevo, which is a popular dance, or how do you say folkloric dance in Recife, and we were mixing, like we were using frevo to teach physics. And why do I want to show this? Because answering to Victor's question, that I don't think he's here, but what should we do to have a more diverse environment in the academia? I think we should be able to convince students, and not only students from some specific background, but all the students that doing science is nice, that physics is funny. So of course we have to guarantee the conditions for these people, like for all the students to be able to enter the university, to stay in the university, but I think also we have to convince the students that physics is a cool thing. So it's a very short, I know that I'm already out of time, but it's 3 minutes, and I'm sorry that it's in Portuguese and we haven't translated it, but if you want to understand it better later and don't understand what they are saying, just ask me, okay? So let's see. This is what P2. Charles told me here. What should I do here? Putz, como é que conecta esse cabo aqui?
9 errors.
Alguém sabe?
9 errors that others.
Coitada da Bárbara, foi exposta, coitada. Por que someone help me here? Because I wanted to have the sound. Onde que será que conecta? Tirar essa casinha. Sim. Ele pega? Tá. Quer que eu feche?
Full screen.
But we really need sound. Well, if not, I can just present it later.
We can sing.
No, it's because the student is saying it at some point. Posso apertar play?
Ela estava falando sobre educação física, mas aí depois que eu peguei o conceito, assim, opa física, foi muito interessante, porque eu nunca fui ligada a essa matéria, e aí foi um jeito que eu estava me vendo respondendo mentalmente as questões que ela estava levantando.
Essa questão do corpo com a música e com a teoria da física, acho perfeito. A combinação é perfeita. Muitas vezes a escola do ensino médio não trata alguns assuntos, né, como a questão da autoestima, do corpo, autoconhecimento, e daí você vê seu corpo, né, do jeito que ele é.
Pra gente que é físico, a gente vê física em todo lugar, né? Então, se você for pensar como a física, no fim das contas, ela está explicando a natureza. Para os alunos é isso, é um pouco chamar essa atenção. Olha que na dança eu preciso de física. Se eu quero fazer um passo, né, que é o leque que a gente brincou, eu tenho que colocar mais força ou menos força. Às vezes esses conceitos ficam meio misturados, a velocidade e a força. Não foi à toa que a gente tentou pensar em passos que separam um pouco esses conceitos, porque às vezes também tem essa coisa de achar que a gente está estudando isso, mas não serve para nada, né? A gente ouve muito isso, matemática não serve para nada, física não serve para nada. Estou aqui decorando e é mostrar que não. Ela tá. O mundo, se a gente quiser entender o mundo à nossa volta, a gente vai precisar de entender física.
Eu acredito que foi uma experiência maravilhosa para todos os alunos. Você poder estudar física e ao mesmo tempo aprender sobre a cultura maravilhosa que é o frevo é algo inovador.
E quando a gente pensa em frevo, a gente pode pensar com um corpo isolado, fora do contexto, mas aí quando a gente contextualiza, entende essa história, esses movimentos acontecem de que forma, por que eles estão acontecendo, quem foram essas pessoas que inicialmente inventaram essa dança, então eram corpos negros, que muitas vezes foram sido escravizados durante anos, não somente essa geração, mas a anterior. O frevo não é somente uma dança do jeito que a gente vê hoje, não sei o quê, é também uma forma de expressão que reafirma a origem da gente. Quando a gente começa a associar o corpo, a história e também elementos da física, é como se a gente não separasse as coisas, saca? É como se, na verdade, a gente tivesse um mundo e todos esses elementos, eles estão aqui presentes no mesmo instante.
Há bastante tempo venho estudando e tentando implementar metodologias ativas no ensino de física, em que você realmente tem uma mão na massa e os alunos vão explorando os conceitos ao invés de a gente dar os conceitos prontos para eles. A gente tenta trazer interesse à física, um interesse diferente, universidade sair de dentro da universidade. Porque a gente precisa chegar na comunidade, precisa dizer o que a gente está fazendo lá dentro da universidade.
É uma questão de raça e classe, então a gente quer muito trazer o conhecimento para todo mundo, a ciência de vocês, o futuro está nas mãos de vocês. Vocês são protagonistas. Usar o seu corpo, né, como uma forma de protesto e de protagonismo e usar somente o seu conhecimento para ir além do que está aí hoje posto para você.
Questions? Yeah,
what were some of the things about physics that you like use with the students? Because I really like dancing also, and really like forró and stuff like that. And every time that I'm dancing at the university, the teacher guys know that I'm a physicist. And so they also lesson like stuff to put on, so like precession, to bend your body, you're going to fall, and stuff like that. What were the things that you used, like physical concepts?
Okay, we were not really like in understanding the movement of the body, we're more using the steps like the tesoura, the frevo language to try to understand, like differentiate velocity and force, as I said, because sometimes we are just like in the same position and then, okay, what is the velocity? And then we were at some point understanding, okay, we don't have any velocity here, but wow, but is it easy to do this movement or not? So it was more like these things, not really understanding, oh, okay, why do if I want to do a spin, if I need to get my body closer, or these things we were not, because we thought, we wanted to keep it as simple as possible, and we wanted also like people, something different, like really them to dance, than to really just talk about physics. And we wanted more than to dance and to feel like comfortable about being there, than to really like, I will have to understand here, velocity is, so yeah. But there is a very nice article from Ciência Hoje, Carolina wrote. Carolina was a student in this community, but she's not anymore. And about dancing, physics and dance. And then she's analyzing these things and explaining this in a way for children. It's really nice. Yeah.
Okay, people, I think that we should finish here and with a very nice round of applause for
And now we have about half an hour of break.